In this video, we're going to analyze a titration involving a strong acid and a weak base. So the experimental setup for this would look something like this. You would have your burette, and in the burette you would have your strong acid. Your weak base would be contained in your flask. So you would be adding your acid to the weak base. A titration curve for a strong acid weak base titration would look something like this. You would start out at a relatively high pH since you have only a base in your flask, and then as you add the acid you would get an initial fall in the pH. It would kind of level out, and then it would drop dramatically near the equivalence point, and then it would become level off as you continue to add acid. For this type of titration, your equivalence point is always going to be below 7.0. So for a strong acid weak base titration, we need to be able to calculate the pH of the solution at the following points. We need to be able to calculate the pH before the addition of any acid, so when we just have the base, after the addition of acid but before the equivalence point. We need to be able to calculate the pH at the equivalence point, and then calculate the pH after the equivalence point. Each of these points in the titration requires a different strategy for calculating the pH. So we're going to have a different video for each of these points in our titration. For this video, we are going to analyze how to calculate the pH of our solution before the addition of any acid. So on our titration curve, we would be calculating the pH right here at the point before we began the titration, before we began to add any of our strong acid. So calculating the pH for a strong acid weak base titration before the addition of any acid involves certain steps. First thing you need to be able to do is write the correct chemical equation. Next, you need to be able to set up an ice table. Then, since we have a weak base, we would use a Kb expression and plug in our equilibrium values from our ice table, and we would solve for the concentration of OH-. We could then convert OH- into H3O plus concentration and solve for the pH. So in this example, we're going to be looking at a titration like this. We would start out with 30 milliliters of our 0.200 molar ammonia. So we have our weak base in our flask. Here's the Kb for ammonia. And we're going to be titrating 0.300 molar HCl. Now, here's our problem. We want to calculate the pH of our solution before we begin adding any of our HCl. So before I go through it, pause the video and see if you can calculate the pH before the addition of any HCl. Look at the steps we just went over and you give it a try. Pause the video. Okay, so to calculate the pH before we add any HCl, the first thing I have to be able to do is write the correct chemical equation. Now, before we add our strong acid, all that we have in our flask is just ammonia and water. So our equation would look like this. We have aqueous ammonia plus our water, and that's going to eventually come to equilibrium, and we're going to form our conjugate acid and our conjugate base. So once we have our equation, we can set up an ice table now. So our ice table would look something like this. Our initial concentration, again, this was given in the problem, is 0.200 molar ammonia. Our water is a pure liquid, so we don't have to worry about its concentration. And we have initially, we have 0 molar ammonium and 0 molar hydroxide. As the reaction comes to equilibrium, our concentration of ammonia will decrease, minus X, and our concentrations of ammonium and hydroxide will increase by plus X. Again, this is because of our stoichiometry. Everything is a 1-to-1 ratio. Our equilibrium concentration of ammonia will be our initial minus our change, X, and our equilibrium over here will be X and X. So now, once we have our ice table, we can set up a Kb expression. Again, we use Kb because we're dealing with a weak base. and we can plug in those equilibrium concentrations. So our Kb expression would look like this: our concentration of reactants divided by our concentration of our concentration of products divided by our concentration of our reactant. Again, we don't include water in our equilibrium expression. Now we plug in our equilibrium values. Here's the Kb value that was given in the problem: xx divided by 0.200 minus x. We can make the assumption that x is negligible, and that's going to simplify our expression. And now we just solve for x. And we get x is 1.9 times 10 to the minus 3 molar. Now remember, x is equal to the concentration of OH minus. It's also equal to the concentration of ammonium, but here we're wanting to get the pH. So our concentration of OH minus is 1.9 times 10 to the minus 3. So our final step, we just have to convert our OH minus into H3O plus, and that will allow us to solve for pH. So our concentration of OH minus, we just solve for that. We can convert OH minus concentration into H3O plus by dividing Kw by OH minus concentration. We can plug in our values here. We know Kw, we know our OH minus, so we get our H3Os, our hydronium ion concentration is 5.3 times 10 to the minus 12 molar. And then we can take the negative log of that in order to get the pH. So you can see, as expected, our initial pH before we begin our titration, it should be very basic because we just have ammonia in water. And our pH is indeed very basic, 11.28. So be sure that you can calculate the pH of any titration before you begin to add the titrant. In this case, become familiar with these steps that we covered in the video.